Morning, everyone. It's great to see a full lecture hall. Those on Zoom should come to lecture. It's exciting here. Today, we're going to do some more math, but it's going to be fun because we're going to connect it back to this amazing result that when I first taught this class, I just jumped straight to the amazing result and no one followed it. This time, hopefully you will follow it. I will try to pause. We have some interactive Slidos, so it should be fun today. Should be a good lecture. So let's jump in. Please join the Slido if you've not. This guy go away. All right. So today we're going to build on the work we did on Tuesday to talk about estimators and then reason about this fundamental trade-off between bias and variance. We'll get some exercise, some practice using the mathematical concepts we've already introduced, which will be good. And hopefully, by the end of the lecture, you'll appreciate this trade-off and why we have to optimize for it and why it is sort of fundamental to building models, to machine learning, to estimation, in some sense to all the things we do when we reason about the world in data science. Brief recap. So last lecture was fast. We went through some challenging mathematical concepts that are pretty essential. Again, these are concepts you will see if you go on to take Stat 140, but we needed to see these concepts in order to show you what I want to show you today. Also, having seen them a couple times will make it so that when you see them in the future, it'll be a little bit easier. The first that we talked about was the definition of an expectation. As this, essentially, I take a random variable and I want to compute the mean, if you will, of that random variable by looking at the probability of each of the possible values that variable takes times the value that it takes. We write this as expectation. It's worth noting that, unfortunately, in my slide style, sometimes we write expectation with like this, double lines, and sometimes I'll just write it like this. It'll be pretty clear. I think I'll use square brackets always to denote expectations. Hopefully, in the exams and stuff, it'll be also clear as well. Right, so expectation, again, the other important thing is a function from a variable to a number, constant. We also introduced the variance, which is the expected square difference, the variable. Again, a function from a random variable to a number. And we introduced this computationally easier method to compute the variance. If you've already computed the expectation, you square it, and then you subtract that from the expectation of x squared, which you can calculate by, again, using this equation up here, but changing this to squared. Yeah. Slide. All right. Basic ideas, but essential. Then we introduced some identities, which are good to know. And I use these in my research today. These are really standard identities and really powerful. In particular, this linearity of expectation, very useful. This is saying if I have a constant, a random variable, and a constant here, and I take the expectation of that, then it's a times the expectation of a random variable plus the constant. So constants pop out of our expectations. Linear operations pop out of our expectation. Variance is a little bit trickier. So variance of a constant is 0. Constants don't change. So that goes away. So there's there's a 0 here. And then the variance of ax is a squared times variance of x. So we pull out that constant, we're going to multiply by the square of it. Some more interesting identities. Again, this one I use a lot. Linear of expectation. I can take the expectation of two random variables. Related, not related, doesn't matter. Any random variables. The sum of them is the sum of the expectations. Very useful. The other one, again, variance is a little bit trickier. Variance of two variables added together is the sum of the variance of the variables plus this term that accounts for the covariance, the dependence between the variables. We showed that equation in last lecture. All right. Useful identities. We'll walk through how to use them in a moment. Are there questions? What am I using in research? Very good question. Often when I'm trying to reason about something that I don't understand, a random process, It's easier for me to think of it as a bunch of little random processes working together. So I'm trying to schedule some queuing algorithm, and I have a bunch of things happening. And I want to look at the sum of those things happening. Well, I build variables to represent the little things because I know how to reason about them. If it's a coin flip or it's an interesting distribution. Well, what's the behavior of the whole thing? Add them up. What's the expected value of that? Expectation. So we use these a lot to model complex things. And you'll see it. I'll do it today for this fundamental result. Other questions? Right. So it turns out I needed one more identity, which I forgot about. So I'm going to give you one more useful identity for expectations. I'll derive it here, and we'll use it in the end of lecture today. So what is the expectation of the product of two random variables? In general, this is actually hard to figure out. But if we assume that they are independent random variables, then this expectation factors like this. In previous versions of this class, we don't go through the proofs in lecture. I like to go through the proofs, partly because I'm bad at math. And for me, it helps to understand what's going on. So I want to walk through this proof. I wrote it out. I'm not as good as the previous lecture at drawing on slides. So let me just walk through the steps here. So let's look at the definition of the expectation of x and y. It's two variables, so I got to sum over two things. I'm multiplying x times y, so it's x times y here. And then I take the probability of x and y. It's the joint probability of the probability of two variables. It's saying the probability of all possible outcomes for the pair of variables. Because it's independent, definition of expectation, because these are independent, key definition of independence, I can break this probability into two separate probabilities. Definition of independence. Now I have a sum, and this is algebra. So this y here doesn't depend. Let me clear this out. This y here and this thing they're independent, so I can slide this over here, just rearranging my multiplication. This summation doesn't interact with this or this term, so I can slide this summation over here too. So I get something that looks like this. I have this summation over the y, the summation over the x. And I put parentheses here to make that really clear. So it's algebra. This is the definition of the expectation of x. This is the definition of the expectation of y. So I get the expectation of x times the expectation of y. Questions? Question, I'll ask you a question. Is it helpful for me to go through these proofs in lecture? It says, yeah. It says, meh, I believe you. Thank you for the belief, but okay, so it is helpful. I'll continue to try to do the definition. Done. Okay, so I gave one more important identity right here. So we're going to use that in this lecture. All right, questions here. Pause. Let's keep going. Ooh, an exercise. Okay, so in previous versions of this class, Nargis has a better budget and she brings in money. I couldn't find money for this one. So we'll do a betting exercise. It'll be mostly philosophical. So someone walks up to you and says, you know, we're going to play a game. I have two $10 bills. Actually, I have a bunch of $1 bills. Yeah, that's it. And I'm going to flip a coin 20 times. And you get to pick which of these payouts do you want. Okay. So the coin is going to be flipped 20 times. It's going to land heads. That's going to be a 1, and tails 0. It's a fair coin. Just draw on a slide. So heads 1, tails 0, fair coin. You can get this. So if it lands heads the first time, you get $10, and heads the second time, you get $10 more. It's a $20 deal. That's one option. Another option you can choose. You get a bunch of $1 bills, and I flip each coin. Every time it lands heads, you get another $1 bill. The last one, for those who like to go big on the first coin flip, I flip the coin once, it lands heads, you get all $20, tails, you get nothing. So first, do you see how I'm modeling this as random variables? These are random variables. This equation here is a function. This is a random variable too. It's a function of these random variables. Which one do you want? And this is a Slido. What do people want? Which bet do you take? What's the good bet? All in? How do you analyze this? So you're thinking, what are the tools we have? All right. Let's see what people said. So you all chose B. I like that. Why B? Someone have a reason why B? Yeah. B has the lowest variance. How do we know that? We figured it out. Bernoulli's. Yeah, so we're going to analyze that in a moment. Other thoughts? Yeah. Oh, that's good. So you're thinking about the identities. One of the identities said if I multiply by a random variable, I'm going to square that variable to get the variance. I guess everyone's kind of clued in. I want the low variance bet. Wait, why do you want the low variance bet? Don't I want the bet with the highest return? I want the bet with the highest return, maybe. Maybe I want some combination of the two. Does anyone have a thought on the returns? Are they all the same return? What would that mean? What term do we have so far to capture that concept? Expectation, right? Good. So what is the expectation of each of these? 10. We should derive that in a second too. That'll be easy, I think. Hopefully. All right, so they're all the same bets. So then you guys, oh, okay, so they're all the same outcome, but I want the one with lowest variance. That makes sense. And use some clever ideas about the rationale. I could derive it, which we'll do. Or I could just look at the identities and say, remember, this one here, I'm going to take 20 squared to get the variance of this thing, this y. Seems pretty big. 10 squared, 10 squared. This is just the sum, but they're independent. What happens is sum of independent variables? Sum of the variances. Okay, so that does feel smaller. All right, so you all decided you want the safest bet for 10, which is probably what I would have chosen too. Some of you were risk seekers. Maybe it's more fun. That one flip, go big on the first coin. All right, so that was the Slido. People filled it out. Let's do a demo, because I didn't do a demo last time. There you go. So I said this last time that when we're solving these problems in the real world, and again, in my research, I use these exact techniques we cover in this class. I use them often. I will try to do the analysis using the analytic tools that we've introduced. Sometimes I'm lazy and I won't. Sometimes I'm not just lazy, I can't. So the math is too hard. So what do I do in those situations? I open up a Jupyter notebook and I start simulating. Yeah, if I say, what's the product of all these coin flips? What's that outcome? I don't know how to analyze that yet. Maybe I do. But we do know how to do that. If I make them correlated, now I don't know how to do it anymore, right? So if I flip a coin and it picks the next coin, it gets harder, right? And so in these situations, we use simulations. So let me just briefly show you how you would do this without math, without analytic math, instead using just simulation. All right, so these are the three variables I'm simulating: YA, YB, YC. I'm going to make a probability distribution in pandas. So I have my table. This is my Bernoulli random variable. It's 1 with 0.5 and 0.5. Could have changed p. It'd be more interesting if I had a different p value. We could do the analysis, but we're not going to do that today. We stick with the standard fair coin. How do I simulate YA? There's an important idea here. If I want to simulate some function of random variables, this is the cool part. I just simulate the random variables, and then I compute the function. But I actually want to simulate a scenario. So I'm not going to simulate just x1 and x2. I want to simulate x1 and x2 many times. So I'm going to simulate. I invite someone up to stage. I flip the coin twice. That's one event. That's one simulation, or one sample in my simulation. Then I invite someone else up again. I flip the coin twice, and so on. So I need lots of pairs of x1, x2 to compute YA. So there's a couple ways to do this. I'll show you something we've already seen. So I can sample from a data frame. So I have my data frame here. I'm going to sample 10 times. Probably want more than that. I'm going to choose my weights to be this column here, the weights column. I want the replacement true, because when I sample a row, I'm going to put it back so I can flip it again. And I want the x value. That's sampling from my data frame. Does that look right? Look at all those ones in a row. Is that real? Does that happen? Is it a fair coin? Yeah. Could it all be all ones? It could be. A lot of ones there. A lot of zeros there, right? So kind of reflecting back on something we talked about last lecture, if I give you a small sample, it's hard to say what P is, right? You need bigger samples. And there's machinery for dealing with that, which maybe we'll try to touch on at the end of the class. In practice, you generally get a larger sample. And in these experiments, I'll use 10,000. Here's big. So 10,000 simulations. I'm going to show you another way to do this Bernoulli thing. So when I'm doing this in my research, it's too much work to make a data frame. There's a simpler way to do this. So I'm going to sample a different random variable and then apply a function to that random variable. Let's talk about that. So I'm going to sample. Let's look at this first. I'm going to sample 10,000 rand 10,000 by 2. What is that doing? That's making a matrix of a continuous random variable where I've sampled independently one of these rows. It's a number between 0 and 1. Uniform distribution between 0 and 1. I pull a number between 0 and 1. But I want to turn that into a coin flip. So I say that it's less than P. That's the probability of heads. So 50% of the time, it's going to be less than 0.5. 50% of the time, it's greater than 0.5. If I said chance of heads was, if I said it was 0.75, now 75% of the time, this thing is true, lands heads. But I want a fair coin. So I made a function of random variables to make my new random variable. There's a matrix of x1, x2, x1, x2, x1, x2, 10,000 times. Now I want a function of that random variable. So I'm going to take, I said you get $10 for every heads. So $10 times true is 10. $10 times false is 0. I'm going to sum over the first axis. That's confusing. So if I sum over the 0th axis, I'd be summing this matrix down the rows, but I want to sum across. So I have 10,000 numbers. So I'm summing horizontally. Let's see what this looks like. And I'm going to put this in a data frame. We'll just do it outside here first. Okay, so that made a giant array of 10,000 numbers, which were the outcomes of my 10,000 trials. That was done by taking the sum along the columns. Just actually draw this really quickly. So just to tell you what I'm doing, I made this matrix. It looks like this. By the way, when I'm doing research, I also tend to draw pictures, especially when working with mathematical concepts. I encourage you to do that if you're getting confused. So this says, 10, 0. This maybe got 10, 10, so on. I want to sum along this dimension, so I get just one giant thing, which looks like 10, 20, and so on, right? So I just did. Okay, and I put this in a data frame. And now, all right. I'm going to analyze these, but let's go ahead and compute the rest of them. So that was how to make the first one. Let's do the same thing again. So we repeat this practice. So now I'm going to make 20 of these flips. I'm going to multiply by 1 because you get $1 for each successful flip. And then I'm going to sum again across the now 20 separate columns. Flips again. Make that choice B. Let's do choice C. This one's easy. One flip, so I'm just going to draw one coin. I'm going to do this n times. And you get $20 for that. It's choice C. All right. So now I have a table with 10,000 simulations of each of these different scenarios. Jump into some visualizations. Let's look at the visualizations first. So this is a histogram of that distribution. So it's a histogram of the distribution of YA, YB, and YC. And already you see that your choice of B is much more clustered around 10. YA has some more mass around 10. There's a couple options, a couple ways to get 10, but has some chance of getting nothing and some chance of getting something, quite a bit, 20. And then option C, the high risk option, is you either get nothing or everything. Okay? So I simulated distribution. I'd look at this and go, okay, which bet do I want? Well, if I'm a risk averse person and I really want that 10, this seems like a good bet. Walk away with $10. Likely. Okay. We can also use that same data to do calculations. You take the sample mean, which is very close to the expectation. Not quite what we compute for the expectation because it's a sample. And really, really large, it gets really close. How close does it get? We talked about that in the last lecture. So the standard deviation has the square root law, so 1 over the square root of n. So as n gets bigger, it gets closer and closer by 1 over the square root of n. You look at the variance. Some of you bet variance of choice B, that summation version, was the lowest variance. Good choice, definitely the lowest. Choice A was a little higher, and choice C was quite high. Right? It was practically 10 squared. Right? Okay. What's left? Let's look at the derivations. Let's go to the derivations. All right. So we did that. So now let's try to work through these analytically. All right. So here's option A, option B, and option C. Let's compute the expectation first. All right. So we're going to use these identities up here. All right. So the expectation of A should be, I take probability of getting 10. This is actually using linear of expectation. So I take 10 times the expectation of x1 and 10 times the expectation of x2. Remember, for Bernoulli's, the expectation of a Bernoulli random variable is just p. So this is 0.5. And also for the Bernoulli random variable, we're going to use variance is p times 1 minus p. 2. Oh, sorry. So let's do the expectation of b. So this is, again, this trick that, again, I use all the time in my research. Is I'm going to take the expectation of the sum as the sum of the expectations. So I slide my expectation in, each one's 0.5. So I get 20 times 0.5, or 10. And then the last one, again, linear expectation. So I take the expectation of this one, and that's 0.5. So again, I get 10. So as you said earlier, they all have the same expectation, same payout. You change p, maybe they don't. I don't know. Do the analysis again. All right, how about the variance? So we work through this. So we're going to use this identity here because it's very helpful. These are all independent random variables, so we don't have to worry about covariance term. So actually, I guess we use this as well. Not to worry about the covariance term. All right, so these are independent. So I take the variance of, let's clear this, the variance of x1, variance of x2. They multiply it by 10 squared, 10 squared, right? So that's good, 0.25, and that gives me a variance of about 50, which is roughly what we calculated before. Do this for variance of y. So I'm going to, again, take the sum of the variances. So 0.25 added 20 times, so 20. So you get 20 times 0.25, which is 5. 5. Okay. And the last one, again, I'll use this identity up here. So the variance of 20, I should have said this is 20 squared, but then I need to multiply by the variance of the variable itself. So that's going to bring it back down. That's how we got 100. All right, that was fast. Are there questions? I'm going to again ask a question. Who's feeling pretty comfortable with this stuff at this point? Okay, who's not? Which would be very reasonable because this is hard stuff. So I will say when I started doing this, I was often, this was hard for me to get. So I had to go back over and exercise it a bunch of times. Work through these would be good, and then hopefully in discussion you get a chance to practice these as well. Okay. Keep raising on Zoom. All right. Let's keep going. So I did have the standard deviation, but that's just take the square root of the previous numbers, so not as exciting. Actually, I should ask, why standard deviation? Why do we talk about that? It's important. Variance, standard deviation, they're basically the same thing. One's a square root of the other. Here's why, and I wish my grad students would listen to this because they do this to me all the time. They go, oh, I got a squared error of x. I'm like, okay, What's the units of it? It's in, what were they calculating recently? It's like time squared. Like, okay, I don't know what second squareds are. Like, I can't think about that. Take the square root of it, it's in seconds. So when people present a number to you and say the variance of this variable is something large, you're like, I don't know how to reason about that space of numbers. When I take the square root, it's back in a regular unit system. So often you're trying to think about the numbers and put them in contrast. So you're like, I'm off by 20 seconds squared. Hard to think about. You reduce that down to the square root. Okay, I'm off by a few seconds. I see what's going on. So we often like to think about the numbers in terms of these square roots, but the math, all the calculations are easier to do when we think about the variance. So these identities, if I extend them to standard deviations, they get weird because I have to take square roots of sums of variables and stuff. Okay, so that's why we have that other term. All right, and the last big part of last lecture, which is now the focus of this lecture, is this idea of going from some population to some sample, actually, sorry, from a sampling frame, which we sample, to some sample, and being able to compute things on the sample, and then draw conclusions about the population this way, which I think I've built in on the next slide. Okay, and so we already did in the last lecture the sample mean. It relates to the population mean. Today, we're going to talk about predictions, which is pretty crazy. We worked to this X bar is a sample mean, and we looked at how it relates to the population mean, the parameter that you would have gotten if you computed the thing on the entire population. This is, of course, a random variable because our sample is random, so the choice of X size is random. All right, this was a square root law that we introduced at the very end of last lecture. It's also introduced in Data 8. It's an important, big concept. We present it in a semi-hand-wavingly fashion, though I will say in the last lecture, we did derive this. You should work through that. So what is the expectation of this sum, this X bar? And you can show that if you knew the population mean was mu, that it would in fact be that. You can do a similar analysis for the standard deviation and show that the standard deviation, I think we did this in the last lecture as well, the standard deviation is this. And that's saying that X bar, this random variable, when I sample it, the variation of that random variable X bar, that estimate of the mean, gets smaller as my sample gets bigger by the square root of n. And it's kind of absolute scale as a function of the variability of the thing that I'm sampling from. So if I'm looking at, I don't know, what's something that's not variable? Heights. If I look at heights of students in the class, maybe that's got a small sigma. So the sample means are going to change very little depending on the number of students I sample. If I look at grades or something, hopefully that's also the variance, but they say that was a wide variance. Then I take a small sample, I'll see much greater variability. So that's what this sigma is describing. The population's true variability. Here's kind of two cute pictures of how this converges. So we say that it converges, what do we say here? To a roughly normal distribution, maybe it's on the slide. As I get this sample mean X bar, so this distribution of X bar, as I increase n, it gets more pointy and more concentrated around mu. This is mu right here. It's centered on mu. Right. That's a big idea, right? That I can start to reason about what the population, what the distribution of my sample statistic is as a function of the population. And I can even show that on average, this thing is going to look like the thing that I'm trying to compute, that it has the expected value of the mean. And then it's going to get closer and closer as I get more data. Those are pretty exciting results. That gives us hope for our ability to reason about the world from just a sample. But we'll do more today. All right. So we said we're taking a sample from the population. This is our sampling process. We're going to generalize this idea and say it's not just the mean, but there's some sample statistic that we compute on our sample. It's a function of our sample. And then there's some sample statistic that we could have computed on the population, which is a population parameter. It's a function. If we had the whole population, we run that code on the whole population, it gives us theta. But we only had a sample, so we have theta hat. And we want to know, can we estimate this parameter from this parameter? That's our goal. Here it is. One important point of notation is we're going to use this term hat as an estimator. This is an estimate. When you put a hat on a variable, it's probably a random variable, right? So I put a hat on a parameter here. This theta hat, it's a function of our sample. Our sample is random, so this is a random variable. And I want to answer questions about how this relates, how this theta hat here relates to this theta here. We already did this once with the sample mean. Right. So can we use the estimator? It's this process of computing this, the estimator, to estimate the parameter of the true population. And we already did this once with the sample mean statistic, and we use that to estimate the population mean. So in that case, this was mu, and our statistic here was X bar. Maybe you all can guess where this is going. What if theta is our model? What if theta is our model predictions? Can we say something about how our model or our model predictions relates to the population? That's today. All right. Some important questions. So how do we know that our estimator is good, right? There's sort of three questions that we've already set up in lecture. One, we've already talked about error. So can I compute the expected error of my estimator? Good. How close is it on average? It's kind of like the expectation is, do I expect the estimator to be the thing, the parameter? I'd like to say that the expectation of theta hat equals theta. Wouldn't that be nice? Sometimes you can. Sometimes you can't. Sometimes you don't want that to be true. Talk about that in a moment. All right, and the last thing, which kind of relates to what I just said, is how variable is the spread? We already talked about this. X bar has this property that its variance of this is sigma squared over n. Standard deviation. Yeah, the variance is that square root of that is the standard deviation. Right. So we already said something about the spread of X bar. Can I say something again more general about any parameter? I'm going to try to do that for a special class of parameters in a moment. All right, so now I say previously when I taught this, I didn't do the notation well. This time around, you have some concepts already to answer some of these questions. So how close is our parameter? So we already talked about this mean squared error, and that's this expectation. Kind of the analog to the mean squared error computed on the data is this expectation. Wouldn't it be nice to be able to say something about bound this quantity? Bias. When we talk about bias here in the statistical sense, we're asking, what is the expected difference between this and this? This is our estimate. This is the true value. This is our estimate here. Okay. If I take this expectation, we already have a useful identity. What's the expectation of a constant? The constant. So we just get this, right? Linear of expectation of a constant. So you have questions on Zoom. Let me pause for a second here. Can they ask questions on Slido as well? Please ask questions on Slido. Staff will answer it. And if there are questions that they want my help to answer, they'll let me know. Awesome. OK. Bias. Check. How about the spread? We have a term for that, too. Oh, I should say this. OK. An important detail. There's a specific class of models when I can say that this equals 0. That is an unbiased estimator. That means that the expected value of the thing equals the thing. The expected value of my sample parameter equals the population parameter. That's an unbiased estimator. That's often something we seek, though we won't always be able to get that. And sometimes we don't actually even want that. All right. And the last thing to reason about is the variance. So what is the spread of my answer? And we've already defined variance. This is the definition of variance right here. So how much does the sample vary from its expectation? I'm going to tell you the whole punchline for the lecture briefly on this slide. I want to make this small. I also want to make this small. And I'm going to show you that this MSE is equal to some combination of these two things, which is crazy. So we can actually say something about the error is a function of the bias and the variance, which gets us to this fundamental bias-variance trade-off. Sometimes making this one smaller is going to make this one bigger. We're going to find the right combination. Okay. All right, let's go to the next slide. Oh, cool, analogy. So as a hobby, I'm an archer. I'm a very bad archer, but I like to go to the local public archery range. Archery is a great way to demonstrate this concept. So let's try to do this. Here's a target. archery, you get to shoot an end of 6 arrows at your target. Those are random. You try your best to hit the center. Let's say the center is the parameter, theta. That's the true value. Each of these arrows is my guess. So this could be like this is my first theta hat 1. I try again, fix my bow a little bit. That's theta hat 2, so on. I get 6 shots on target. All right. Sporting analogy. Any archers? I don't expect hands, but it'd be great. Okay. Bummer. All right, so that is the setup. Let's, instead of me explaining this analogy, I want to see if you can guess how I might relate bias and variance to this picture. So which target demonstrates high variance and low bias? And to answer that question, create a Slido. You tell me. Then we can ask which one is my target. All right. So let's see what people said. So again, target demonstrates high variance, low bias. Wow, I didn't even explain the analogy and you already got it. Okay, so everyone said A. Let's talk about that. Why is it A? People finish guessing. Does anyone have an answer to why it's A? Let me bring it. I think if I go back, you can keep answering, right? You can still answer. Yeah, okay. Why A? Yeah. Yeah, so high variance, large spread, good. And then low bias means it should be around the true center. So that's A, correct. High variance, low bias. What does everyone want when doing archery? You want low bias, low variance, right? Again, some of the things, that's if we can bring both down, that'd be great. We want something that's just clustered on the target. This is me in my archery today. So high variance, high bias. I can't aim consistently, and I don't even aim in the right direction, right? Bias is how far off am I from the center on average. And then variance is how spread out am I. So spread out and not hitting the center. Very good. Okay. So here's a more detailed version of this picture. So when you're trying to think about bias and variance and how they relate to estimation, to matching your hitting the target with your theta hat from your sample to the true target theta, this is a good picture to have in your mind. It's a good exam question too. Okay. All right, I think that's all I had to say on that. Yes, so now we're gonna do the big thing. We're gonna connect all these concepts and try to make a statement about our predictions as a parameter, which we'll see in a second. All right, so we're gonna pull everything together from the past 2 weeks. We have this equation of how we estimate our theta hat from our random variables, our data. We have n of them, and we tried to minimize a loss. And then we introduced this regularization penalty, which cares just about our choice of parameters, and this hyperparameter that you tune using cross-validation. We can kind of ignore this. This is a constant for now. This is my regularized loss. And I'm trying to choose a theta hat, again, this one, that minimizes this expression. That's my shot at the target. Very good. I get my sample, and I fit something to it. Whoops, that's a terrible drawing. Fit something that looks like this green line here. That's on my sample. So what's kind of neat is at every point on this line, it makes a prediction. So for right here, for this x, I get a prediction. That's my y hat. It's got a hat on it. That's a sort of a parameter. It's a parameter. I'm estimating the value of the thing at that location. But I observed, maybe I go out and measure it, and the value of that location is that. That's the true y. We got to get a little deeper into what it means to be the true y. So let's do that now. So again, to make a prediction, I take my model. This is a parametric model. So really, I'm learning this parameter. That's a hat. And I'm making a prediction. That's another hat. right? And I make that prediction at a specific location X. X, you give me that X at test time. It's not a random variable, it's going to be fixed. You could actually analyze this with the random variable here, but I'm not going to do that for today's lecture. So that's a fix. So I'm asking the question at a fixed location of X. This is the error that I would really like to minimize. Remember that slide earlier, 2 slides ago, maybe? I was saying that there's this mean squared error. This is the mean squared error between the true y and the y hat. Okay. Now, what's a random variable here? I already told you that these are random variables. So that means this is a random variable, which means this is a random variable, which means this is a random variable, and therefore this is a random variable. What about that? How do you know that's a random variable? Because I capitalized it. So probably it's a random variable. Wait, why is that a random variable? So it's the truth. Truth is not random. We're going to make one more assumption to make this lecture as complete as possible. The world has some true underlying function, g. We don't get to see g. Fortunately, we only get to measure things. So we have g, the truth, but then there's some measurement error, observation error. Can't do much about it. Maybe you get a better system to collect data. This is the truth for today's lecture. This is a random variable. It's noise. And that's going to make the thing that we observe, the truth, sort of, also random. So I'm going to model, in the reasoning through this probability exercise, the observation error as well. So there's some uncertainty. Another reason to do that is in practice, sometimes I'll assume a simpler version of G, in which case there's just something I can't explain about the world. And every observation doesn't really follow the G. I don't actually have access to G, so maybe I'll assume the population has a specific form of G. So I definitely want to be able to account for that kind of noise, inability to fit the exact data I see. Okay. All right, so fixed features. So I'm going to look at a test location, a new location that's fixed. G is going to be fixed, so it's not a random variable. That's the truth out there. And then my response, y, is a random variable because of that noise. Make one more important assumption for today's lecture is that noise is IID, so it's all data, all locations have the same noise, and it's independent. So every time I measure something, there's just the standard sensor noise. I'm going to make one more assumption, which is pretty standard, is that the expectation of that noise is 0. It's kind of centered noise. Later on, Thursday's lecture, we'll see why that assumption is especially reasonable in specific use cases. But for now, we'll just assume that's centered noise. It's an important assumption. And the variance of this is some sigma squared, which we don't know. It's fixed. There's a sigma squared variance for all the locations. And that's this deviation from the truth, true line G. Okay. Actually, let me pause here. Any questions? It's an important setup. Slider's going okay? Yeah. Great question. How do you know any of this if we don't know anything about the population? You don't. Here's the cool part. We're going to assume these things. We're going to do some math, and we're going to see that the math depends on the assumptions we made. And from those assumptions, we can see where if I assume something different, I'd get different results. So we don't know these. These are assumptions we're making in our modeling process and these calculations that we're about to do. So we don't typically know the population. If we did, most of this would be unnecessary. We just calculate the answer. So we're going to make assumptions about the population and see, and these are pretty general assumptions. There's some G, I don't know what it is, but it exists. And there's some noise that affects what I measure. I don't know what it is either, but it exists. And I'm just going to assume that on average it's 0. And there's some sigma for which I could bound it by, some constant sigma. All right, any other questions? Yes. Y is what I observed. So when I made my training data set, when I sampled population, I got a person, I got to see their Y. And I measured their Y for that person. I get another person, I get their X, and I ask them, I get their Y. And each of these Ys I get for each person is a noisy measurement of that true G that is part of that person. And now it comes to test time. Got my model, I make a prediction. Someone hands me an X, make a prediction. It's my Y hat. There's a true Y. How close am I to that true Y? I don't know. That's what we're going to try to model. Okay, so the picture, just from previous lectures, is I've got this truth, and then I've got the thing that I'm modeling. This is my model. And here's two versions of my model. If I got these data points here, they fit this crazy polynomial line. This is the model that I predicted. And here is the truth, this hard to see line that's faint. That's the truth. Never get to see that, remember? And then these are my population dots. Again, I didn't get them either. I just got the dot here, the dot here, the dot here, the dot somewhere over here. I got a few dots in my sample. Right? So there's a lot of things I don't know. I want to reason about those using the tools that we have. This purple line here is another version of all the things I sampled here, 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 these dots, and I fit this purple line here. And again, it doesn't match the truth. Here's the truth over here. It's not close, it's all over the place. But it's what I got from my sample. And again, I'm trying to reason about the relationship between this line and the truth, which is hard, as well as this line and all the population points that I would have tested. So if I were to test it here, this is what I see for the population. This is the truth, which again, I don't observe. And I want to know how far am I from here to there. So I'm going to try to analyze. If it's a little confusing, I'm going to draw this in a picture in more detail in a moment. Just to use our previous terminology, this here is an estimate of this. So we're estimating with Y hat, we're estimating Y. And we're using our model to do that. That's our prediction process, is a form of estimation. All right, so now we're ready to do the fancy math. I'm going to go back to this picture because this is what we're going to derive. So long ago, we said this idea is I make my models more complicated. My variance goes up, so I have more variability, but my training error goes down. I can fit my data better. And then there's this validation error, which goes down. And then all of a sudden, because my model is crazy, it starts to go up again. And that was a good guess for my test error, right? I don't get to look at my test error because that's cheating. I get to do that once, but I can do validation error as much as I want. And it's typically a lower bound on my test error, lower guess of what my test error might be. Often pretty close. Right, so that was our setup. And now we're going to formalize this process. Here's a more formal picture of what we're about to show. We're going to talk about model complexity. We're going to talk about the model variance, the variance in our predictions in this case, and the model bias. And we're going to do this in a square sense. You'll see in a moment. And we're going to relate these two things to this test error mathematically. So let's do it. All right, this is the picture I think will hopefully make more sense. So the green curve is the model I fit to my data points here, 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 and here. So I had a few data points. The red curve is the truth. I don't get to see that. And the blue dots are the population. I don't get to see that either. All right, so let's zoom in on just this dotted line here. So I'm going to zoom in on that. Get this picture here. So I have a fixed X that I'm checking at. I predicted Y hat. The population had some Y, which is a noisy observation of some G. Again, I didn't get to see either of these things. And the residual, we've plotted this before in our analysis of regression. This residual, just a difference between our prediction and the truth, the population value. That's this black bar here. Right? And I want to analyze what that is. Let's do it. Okay. There are sources of noise that affect my answer. There's the observation variance, which we'll elaborate on in a second. That's this thing here. There's the model variance, which is the variability in f of theta x. It's the variability in this theta, which comes from my sample. That's going to affect this right here. And then there's also the model bias, which is my model's ability to fit G itself. There's just some inability to fit the complexity underlying G. It's the model bias, which we'll make formal in a second. We're going to try to first draw this in picture form before we do the full derivation. The end result that I will show you, so I'm just going to tell you in advance, is that the risk, this mean squared error that we talked about a moment ago, and I'll formalize in a second, is the sum of the observational variance, that's the noise in our measurement process. We can't do anything about that. The model bias squared, and we'll see why it's squared in a second, plus the model variance. This is a fundamental statement that we can show. So we're going to show that mathematically and pictorially, but we'll first start with pictures. So the model risk is this mathematical concept. It is the squared difference and expectation of our estimate from the y in the population. So that is the residual squared, right? Which is something we've seen before. So we're going to take this residual squared. This is an expectation. So the expectation. And it's over what? What's the source of randomness here? One source of randomness is y because we have this noise. The other source of randomness is y hat because this depends on theta hat, which depended on all of our data, x1 to xn, as well as their y's. Okay. Source of randomness. We're going to compute this expectation again over when we go to make a measurement over all the possible y's we could have seen when we go to actually test the test value y. So it's over new observations for y. Should stop here. There are questions about this setup. This is admittedly a little confusing. We're trying to make statements about a world we don't understand. And we're at least writing down what we'd like to know. We don't yet know how to show this yet. We'd like to know what's this expected difference between our guess and what we'd measure if we go out and measure the population value at a fixed location x. Questions? Why is there observation variance? Why is there random noise? Some people, when they do this exercise, do not do this. So you don't have to model this. You can say, you know what? The truth is G, and whenever you go to see the world, you see the truth. I like to model this because it'll be useful in a future lecture. And because when you go to measure the world, you don't ever get to see the truth, no matter how hard we try. There's always uncertainty. So let's just put that in our analysis. It'll just be an extra term that we can think about as we do the work. Yeah. So this is the risk in expectation over the future. So we're trying to compute this over the risk with respect to all of these sources of randomness. So this is an analytic quality. When we compute the mean squared error, we're computing that with respect to some data. It's a number computed on some data. This too is a number, by the way. This is a number, which is not easy to compute this number. So we're going to try to reason about what makes it. All right. Keep saying this over and over again, but we'll do it one more time. So there's a source of chance error, and these are error just due to variability. And one was this noise in y. It's easy to see because remember, y has this epsilon noise term. That's one source of noise. And of course, there's a source of chance error from the sample we use to train our models. Those are chance error. And then bias is a fixed thing. So this is not a random error. It's not due to randomness alone. It's due to our model being different from the true underlying function g. Let's draw this out. So let's first take a look at, here's g, here's y. Remember, there's some random errors. So this is, we happen to get this epsilon, but if we run the experiment again, or sorry, if we measured the population at a specific location, maybe this is concrete. So I'm testing this new spot. I bring up a person, I ask them a question. They answer something. I ask them a week later, they might answer something different. So there's some variability in how they respond. I go to measure something. I think it's this tall. And then I measure it again with a different instrument, I get some variability in that measurement. So this is just the error in the measurement when I go to do the test. And there's some just inherent spread in what I'd actually see of the truth. That's my first source of chance error. And this is just observational noise. This also shows up in the training process well, but we'll come back to that. It's independent for now. Right, so this is a source of noise that I have to account for. So I get multiple possible observations every time I go to measure something. G is always fixed. The truth is constant. It's just when I go to measure it, I see variability. This is random. The expectation of this thing here is what? This is a constant. This is a random variable. Right, so the expectation of this random variable is 0, so that the expectation of this is just g of x. That's good. And then the variance of this is a constant. So we don't, if I take got a pen here, so the variance of g of x plus epsilon is what? What is that? This is a constant, so we don't have to worry about that. So it's the variance of epsilon, which equals sigma squared. Right, so we have some fixed observational variance. We assume that. Reasons, again, measurement error, missing information acting like noise, another reason we might have this. So we didn't get the full x, so when we go to measure g, we're not really plugging in the right values, so we see different values for g. So, and later on, we'll see when we make some assumptions about the form of g, that this could just be noise and the inability of the model to fit the true g. So we'll come back to that, but generally, let's think about it for now as measurement error. All right, how do we fix this? Try to get more precise measurements. It's one option. Typically, you think of this as beyond your control. This is the error that you just can't get rid of. No matter how good your model is, you're still going to have some error. Think of it as the irreducible error. Sorry. Okay. Model variance. This is a little more complicated. All right. Remember in lecture, we looked at if I fit my model many times with different samples of the data, I'll get different models. I get variability in my models. If I put them all on top of each other, see all these different lines I could have fit. If I think of the spread of this, spread over this space here, that's kind of the variance of those models. At any one point, I have spread. The variance, in fact, I actually have it animated here. So if I take one point in space, I have some spread of the lines that go through that point in space, right? There's this variance in my predictions for the different models I would have gotten if I had different samples of my data. This is the model variance. We're going to find it as just the variance of y hat. So prediction variance at a specific location, x. What is that? No, it's a quantity. We're going to leave it. We're not going to be able to fill this in more detail. That's just a thing that we need to reason about. It's a source of error in our predictions. Reasons for it: different samples lead to different model estimates. Common cause: overfitting. You made your model too complicated. So no matter, depending on the samples you get, when you go to fit your model, you get too much variability in the predictions that you make. How do you fix that? Reduce model complexity, and we taught a tool for that. How do we do this? What's one mechanism we've already covered? Regularization. Regularization. I won't spell it. Yeah, so we already have tools to manage complexity. We should use those tools when we have too much model variance. All right, and the last thing is model bias. So model bias we'll define as the difference between the expected y and g. How far are we from the truth? Which we don't know. So we can't compute this. We can define it. It's model bias. So in this picture here, the truth is this squiggly line. And we decide to fit this with the linear model. So you get this linear model, you get this linear model. Depending on which sample I get, different linear models. Maybe I get one that's like this. Many linear models. If I take the expectation of those models, I get this line right here. And I want the expectation actually at this point in space. If I look here, let me draw this again. So if I take this location right here, and I take the expectation over all of my lines, let's say it predicts this point. The truth is here. So this spread right here is my bias. Questions? Interpreting model bias. Pretty simple. If my bias is positive, I'm overestimating. It's like residuals. my bias is negative, I'm underestimating. If my bias is 0, and this is kind of a special case that we care a lot about, so we often like our models to be unbiased if we can, then we call our model unbiased, or our estimate unbiased. And we can show that certain mathematical procedures for certain kinds of things, like the sample mean, are unbiased. We can prove it. We don't have to know the population. We can answer that question that the estimate will always, in expectation, be the population value. But can we say that about our models in lecture, our linear models? Perhaps not. Let's see. One thing to note, what does regularization introduce in my model? What kind of bias would that be? Is it a bias? Yeah. What's the main difference between the mu and the expectation? So we return back to our discussion on the sample mean. The mu is the population parameter. It is unknown. It is a constant. I have a sample parameter, sample estimate, x bar. That's my sample mean. That's the mean of my sample. How does the sample mean, a random variable, relate to my population parameter? One's a random variable, one's a number. Can't compare them. But if I take the expectation of my sample mean, right? And that's the expectation over all the other ways I could have constructed that sample mean for all the other samples I might have gotten. That is a number. The difference between that number and mu is my bias. Got it? Now, if I bring in regularization, this affects bias. I regularize a model. I make the model biased. I bias the model if I'm doing regularization we covered in class. I'm biasing the model to have smaller and smaller weights. If I turn up the regularization to too large, I've made my model all zeros. My model predicts 0, or maybe just the offset if I didn't regularize that. Right? So I made a very biased model. Let's say I didn't regularize the offset term, the intercept. So then my model just predicts the intercept always for all x, just the intercept. Variance, 0 variance. Very good. The model only predicts one thing ever. So 0 variance. Unfortunately, a lot of bias, and that bias is regression to the mean. So it's going to produce an underestimate of large things and an overestimate of small things. Which we already sort of saw in the discussion around housing, where we have these biases and regression, they tend to regress towards the mean. Okay. Bias. How do we deal with this? Fundamentally, bias is a sign of underfitting. Your model is not complicated enough, not variable enough. We need more variability. We need a richer model. So probably over-regularize, make lambda smaller. Not optimizing the loss adequately. If you're using an optimization procedure like gradient descent, maybe you didn't run it long enough. You ran one step. That's a bias because the model was, you guessed 0 and you took one little step. Model can't be that big, right? So maybe you need to optimize better. In practice, this is typically not a problem for the tools that we use in this class. In some modeling situations, this could still be an issue. You need to improve your optimization procedure. Yeah, in fact, in the wild, if you use most of the tools, again, the ones we teach here, this is usually not the problem. This is usually your problem. Or this. So you're just not modeling the phenomena well enough. Maybe there's other features you should collect to reduce the bias. So remedies, tune your regularization, it's a good idea. Maybe your optimization sometimes, and increase your model complexity by adding features or reasoning about the data that you have more effectively. Okay, so all the pieces. So here's my G. Here's my error from just the noise. This right here, G is the expectation of Y. We already showed that. This is, if I average over all the different kinds of predictions I could make, this is the expectation of Y hat for all the possible ways I could have fit my model. It's also a fixed constant. And this right here is my bias. It's the difference between this and G. Bias right here. And this spread right here, square of this is going to be my variability. So that's the different ways in which I could get, so for a second, the different Y hats that I could get for different kinds of samples. Right. But on the picture, maybe the math will make more sense. Let's try it. Let's jump into the math. Let's do this. All right. So now I'm going to try to break this down. This is the thing that we wanted. This is the piece of our squared error. Remember, if we square this, this is the mean squared error. This is the error that we're trying to ultimately minimize and we'd like to reason about. This is just here, just basic algebra. I'm plugging in the definition of y. So I get this piece here. Now I'm going to do something weird. And every time I teach this, it's a little confusing. So let me just say what I did first and talk about it. I'm going to subtract and add this quantity. That's a number. I'm going to subtract and add the number. What does that mean? Nothing. I'm doing nothing. I'm adding it, and then I'm taking it away. Or I'm going to subtract it, and I'm going to add it back. OK? So I haven't changed the equation, but I put an extra term in it. And that's convenient for an important reason. Now you see something here. This looks a lot like what? That random deviation, that kind of variance term. This looks a lot like the bias term. This looks a lot like the noise term. This is from before. So now I have this difference written in terms of 3 pieces. The 3 pieces, I promised I'd show you relationship to. But I didn't say this difference, I need to do the expectation of this thing squared. So I got some work to do. Let's do that. So that's this model risk. I want to derive this. About to do some algebra. I'm going to go slowly, and I'll pause if people have questions. So again, this is the equation from the previous slide. I haven't changed anything. It's right here. First thing I'm going to do is I'm going to try to make the math easier by replacing all this weird notation with just the letter A. All this stuff here is going to be the letter B, and this little thing here is going to be the letter C. I've chosen the capitalization of these letters to reflect the variableness of them. So A is a random variable. Why is it a random variable? Because this is a random variable. B is not a random variable. Why not? This is a constant, and this is a constant. C is a random variable because this is a random variable. So far, so good. Do one step and we'll pause. I'm computing the model risk, which is this by definition. Rather than having this messy equation up here, I'm going to just use A plus B minus C squared. Notation gone, so I'm just taking A plus B minus C squared. I am terrible at algebra, so I had to double check this, but I believe it is correct. A plus B minus C squared is going to be A squared plus B squared plus C squared. So A squared plus B squared plus C squared minus 2BA minus 2AC minus 2BC. So that's just all the cross terms. Now, I did a little bit more here. I had this expectation. I slid this expectation in because I have a sum of things. The expectation of a sum is a sum of the expectations, right? So I I slid that in here. I have a sum over another term. This got a little bit fancier because I did the x here. I originally had the expectation of 2BA. And rather than show that in the slide, I decided, you know what, this 2B, these guys get to pop out over here because they are constants. So then I have 2B expectation of A. I'm going to stop for a second. Are there questions? This was a little bit of algebra, a lot of algebra actually, and a little bit of linearity of expectation. Yeah. Why didn't I replace it? Great question. I'm silly. I could have gotten rid of this expectation. Why? Well, because B squared is a constant. I didn't need to leave that in. I left that in. I don't know why I left it in. We'll get rid of it in a moment. Fear not. Really made that a later step. Other questions? Yeah. Yes, this is all for one specific x, the test x. The one test point that you have to do well on that one test point. But we're going to show that for all x's, this statement's going to be a true statement. So you could test it again at a different x, and the statement will still hold. But I'm treating x as given, not a random variable. This is the test x. The training x is a random variable, right? The x's and y's they use for training, those are random. This test is fixed. Other questions? Yeah. Why is the model, one more time? Oh, oh no, you're right. Thank you. Hope that's not another slides. Fixing these equations is very hard. To re-render all the way till I can drop it back in. Bummer. Okay, yes, that should be a minus. Good catch. Other questions? Okay, we'll keep going. So we've done some algebra. There's two things here. That was linear expectation. These are the interesting terms. Just back it up right here. This is a typo. All right, so these are my interesting terms here. Just did that. And then these are cross terms. In all great proofs, the cross terms should disappear. So I'm going to get rid of those. So let's work through why those should disappear. I'd like those to go away so that we can show that these first terms, quite clear, I'm going to lose it. It's fine. These are going to be the things that I care about, and I'd like these to disappear. So we're going to derive their disappearance now. All right, so let's work through the cross terms. So step one, we're going to do some substitution. Let's substitute in C. We brought in C. So C is equal to, let's get it here, epsilon. So we put that down here. We do that here as well. So epsilon. What do we know about this one? Expectation of epsilon is 0. We assume that. That's 0. Okay. Oh no, I jumped ahead of myself. All right, what about this? What can I do here? Don't look at the, well, you can see anyways, bummer. All right, so I have the expectation of 2 random variables multiplied. I said I needed an extra identity. Now I need that identity. These are independent random variables, so it is the product of their expectations. So I get this. Now, we said epsilon, the expectation of epsilon, this thing here, is 0. Well, this is also 0, so that's convenient. So this term and this term are gone. Thank you, linear expectation. So they're gone. All right, what's left is this term here. Why is this term 0? I said it was 0. What happens here? Why is that 0? All right, so this is a constant right here. So you have to pop that out. And I'm left with this. It's right here. This, oh, put parentheses around that. This minus this is 0. Right? So the expectation of y hat minus the expectation of y hat is 0. Good. So now all the cross terms are 0. Bravo. One great proof. So we get to get rid of this whole thing. It's gone. And we're left with, oh, it's a bug again. Sorry. Let me fix that. Bummer. Okay. So we're left with, expanded this out equals this. And now I get to apply my expectation reasoning here. So first, plug in A, which is this thing here. So I just plug that in. I'm going to let that be. That's something. Plug in B. We said B is a constant. Someone already pointed this out. I could have gotten rid of this expectation earlier. So I plug in B, but I squared it. So B is squared here. So this is B squared. Good. And I still have my expectation of epsilon squared. And what is epsilon squared? The expectation of epsilon squared, we'll use a couple identities here. It's 0 mean, yeah, it's the variance, right? So just for those who are, one way to show this of epsilon squared would have been the expectation of the epsilon, here. Variance would be expectation minus expectation of epsilon quantity squared. And since this is 0, we just get the variance is equal to, you can't see in this writing, so I won't even try. Yes, if I take this step here, the definition, we said this earlier as well, of epsilon squared is sigma squared. It's the variance. Okay, this is an assumption we stated earlier. Okay. One more step. This right here is the definition of the variance of y hat. So, what time? Y hat minus its expectation squared is the definition of variance. So this thing here is the variance of y hat. And now we have completed the magic. So we have shown, it's more just, this was the model. Oh, man, so much to fix. Okay, this model risk, when written correctly, equals the variance plus, this was the bias squared, plus the observational variance. So what have we shown? We have shown that when writing this under the assumptions we made, there's a true model G, and that we have noisy observations, that this error is a function of these three things. In order to bring the error down, our goal in life, at least in modeling, to bring this risk down, I need to reduce each of these things. Can't control this one much, and unfortunately, these two here fight with each other. This is this fundamental trade-off. And we can show it analytically, that this model risk is a function of the variance of the model and the bias squared. Okay. So interpretation, model risk is an expectation, is therefore a fixed number for a given x. Do we know that number? Generally, no. We can, in some situations, maybe derive a bound on this, or try to calculate or prove that this is 0. We don't know in practice, but we do know that it is a function of these things, and it is a number. This observational variance, typically we can't do much about that. Slide this observational variance here. Observational variance, this thing right here, we can't do much about. So we may not ever get to 0 risk because there's just noise in our data, noise in our observations. This sets up our bias variance trade-off. These are the two terms that I fight, since I can't control this one, to make my model have as low risk as possible. Okay. And we talked already about how we manage this trade-off. So we want to reduce variance by making our model less complicated by regularization or other techniques using fewer features. We also want to reduce bias by making our model more complicated with less regularization and more features. And that is that trade-off curve that we will fight whenever building a model. Already said that. And I believe that is it. So we managed to make it through the whole material. All right, so this is hard stuff. If you are confused, please go back to lecture, come to office hours. I had to cancel my office hours today because I'm supposed to be at a faculty retreat all of today. I moved it to next Thursday morning. So stop by my office hours. I'm happy to explain more of this. I will also add, come to office hours regardless, because I like to talk about basically anything. So just come to office hours. Same with Nargis. So join us at office hours. And I will see you all Thursday in office hours.